Hello. So I'll talk today about symmetry and reflection groups, a bit about the finite groups of unitary matrix. That's going to be the topic. And we'll do a lot of algebra. So we'll discuss about cyclic, diedral groups, permutation groups, reflections, all the things. So very beautiful mathematics. Let's find this, this presentation. Here we go. So symmetry and reflection groups. It's going to be a way of finite groups in general. That's the idea. So let's start with some theory, general theory regarding the finite groups. So first of all, any finite group is a permutation group. That's the same thing, finite groups or permutation groups. Why? Because of this construction of Cayley's. So this is Cayley's theorem. Given a finite group, we can always make it act on itself by the multiplication. So if it has n elements, this means that it's a subgroup of Sn. Now, we can further build on this and say that the finite groups is the same thing as the finite group of orthogonal matrices. So for this, it's enough to see Sn as orthogonal matrices, and that's just clear. I mean, Sn is the permutation group of n things, and these n things you can take whatever n things that ranges you the most. And for this problem, we'll take the n coordinate axis of Rn. So permute them, right? So that's a linear transformation. It's an isometry. I mean, that's the orthonormal basis of Rn, orthogonal basis. It transforms it into itself, but permuted, but it's still orthogonal. So it's an orthogonal transformation, okay? No need to write the formula or anything, it's just orthogonal. So Sn is inside N, and now since we already know that G is inside Sn, if G has n elements, let's run embedding. So G embeds into N. So it's the conclusion of all this, that the finite groups is the same thing as the subgroups of G of Sn, and varies, of course. And the finite subgroups of On and the finite subgroups of Un. So all these n's, they vary, of course. Now the problem somehow, given a finite group B, G was the best embedding that we can find. Best, we'll see in a moment, that's quite subjective. So normally is the one with n being as small as possible, but this is not always the rule. Sometimes it's better to enlarge a bit and have a better understanding of your group. So it's a bit of a philosophical problem. I'd like to understand which what's the embedding where the group can best be studied somehow. We'll see examples in a second, okay? But in general, as a comment, it is a hard problem. It's a so-called representation theory problem. So you have to think of G as if you think of G as an abstract object, then you can represent it as permutations or matrices, orthogonal or unitary. These are so-called representations. And in order to have to come with a final answer to the problem, what you have to do is really representation theory. I mean, look at all these representations, try to understand them all and everything, and that's terribly complicated. So we won't do it today. We'll leave it for later in this course. So today it's going to be a somehow introduction to representation theory without doing abstract things. So let's have this started. We'll first talk about the diedral groups, but before that, cyclic groups. These are the simplest. So consider a cyclic group, I mean, just 10 elements cycling like this. And first of all, we have, you can view them in the plane, okay, as rotations of angles, multiples of 2 pi over n, right? So that's the formula of the rotation of angle t. So plug in this t here, and you get your embedding. Now, we also have an embedding Zn into Rn, because Zn, you see you have this coordinate axis of Rn, so you can cyclically permute them, right? So that's your 20K, you associate this cyclic permutation of the coordinate axis. Of course, in this is here taking modulo n. So this is, you see, with respect to what I was telling you before, normally we should say that 1 is the good embedding because it's in 2 dimensions. This is in n dimensions. But this is better. I mean, definitely it's better to work with this kind of guys than with these 2x2 matrices. So you see, it's very subjective. I think this one is a bit better than this one. Actually, you can do even better. So this was orthogonal. Now, if you look at unitary matrices, you can embed the then into U1 because you see any k corresponds to this power. You take the root of unity of order n, and then it powers this from the cyclic group. So you see, you can, in complex, the formula is extremely simple and the representation is one-dimensional. So this beats everything. So you see, all this is subjective somehow. In the real case, here the dimension is smaller, but this one is better. In complex beats real. I mean, it's not very clear. Anyway, so that's about the cyclic group. Let's get to the other groups. These are the group of symmetries of the n-gons. So at any three, you have how many? 6 symmetries, right? Symmetries with respect to the medians and the rotations. At N4 now, pretty much the same thing happens. So for symmetries, 4 rotations, but there is a subtlety. If you take the square, the rotations, they are of 2 types with respect to this middle things like this, with respect to the diagonals. So you see there is a bit of a difference with these diagonal groups when n is odd and is even. Now, what can we say in general? So yeah, it has 2 n elements, n rotations, which form a copy of the cyclic group. That's just clear. And then symmetries with respect to, and here it's a bit of a discussion. I mean, when it's odd, it's like the triangle or pentagon, wherever you have this kind of median things passing through a vertex and the middle of the opposite edge. And when n is even, you have to kind of think it's like a square. And finally, as the last thing, but we won't get into details here, you see the n has finally a copy of the n inside. And so I'd like to say, well, because it has 10 elements, has already a Zn inside, it should be Zn times Z2, but it's not because this is a billion and Dn is not. But the thing is that if you twist the multiplication of Zn times Z2, you get Dn. So that's your formula, so-called cross product. It's possible to do it. We won't do it now in detail. Now, regarding embeddings of the diedral group, so once again, well, this happens in the plane, right? So here's your embedding. The k rotations are these rotations that we had before for the cyclic groups. And the symmetries with respect to this axis that are ordered like this, zeros first, second, and so on, are given by this formula. So this is these are formulas that you know, right? Now, also we have an embedding dn into n because it's permutations. So actually you can see the n1 there. So take the coordinate axis and take the point at distance 1 from the origin on each axis. This form a regular polygon. So these are the symmetries of this polygon, okay? That's the embedding dn into n. And well, this is definitely better than the first one. I mean, these matrices are can easily get complicated computations, trigonometry, all this, and that's somehow the good embedding. Now, if you pass in a complex case, actually nothing happens because you cannot embed it into U1. U1 being abelian and Dn being not. So, yeah, in this case, unlike what we've seen before for the cyclic group, that's somehow the good embedding here. Okay. Let's discuss the symmetric groups. These are, we'll start to understand how things work when, I mean, the more complicated the group, the less flexibility. And it's by looking at symmetric groups, things like that, that we'll figure out what to do exactly. So first of all, well, it has a factorial element. That's something that you know. You have to choose sigma 1 and choice is sigma 2 and so on. So there are n factorial choices. Now I have an embedding, yeah, just by permuting the coordinate axis of Rn. So that's the formula. And well, there are many formulas and it depends on your taste. Now, if you want to use this notation of EIJs, EIJ is the map which sends J to EI and the rest to 0. EI is the standard basis, of course. That's your formula. So if you apply this to EI, I get a sigma I. And in usual matrix notation, well, it's a 0-1 matrix, of course. So it's Kronecker symbols, and that's symbols, your symbols. So at position ij, we put Kronecker of I sigma of j. Now, what else can be said about these permutation matrices? So first, these are precisely the zero-one matrices, having one on each row, each column. Why? Because you take such a matrix, it's a permutation. You can see there things get permuted, right? That's a permutation. Also, the trace of a permutation matrix, the things on the diagonal, it's the number of ones of the diagonal. And the ones, let's go back, correspond to sigma of I is I. So it's fixed points. So the trace, that's an interesting thing. It's the number of fixed points. Now, because we talked about the trace, let's talk about the determinant too. So here it's interesting to trace and determinant. These are interesting things. So the determinants, of course, it's going to be plus minus 1, and then it's actually the signature of the permutation, minus 1 to the number of inversions. So this is clear. It depends on what's your favorite definition for the determinant. If you say that this is the oriented volume of the parallelepiped formed by the vectors, well, the vectors is just the standard basis, but it's permuted, so it's exactly the orientation there. It's the number of inversions. If your definition for that is the one with the symmetric group, well, you get it right away, of course. So it is just clear, but it depends on which definition you're using. So the consequence of this, when the determinant is 1 is precisely for alternating matrices, those having an even number of inversions. So in group theoretic terms, Sn intersection Syn is the alternating group. Okay, now let's do some more complicated groups. So far was the conclusion. Zn, Dn, too much flexibility there, you can too many things there, but we've seen a few interesting things. For instance, for Zn, that nothing too complex brings you the best representation. For Sn, once again, it's a bit too simple, but we've seen that trace and determinant are interesting things to look at. Now let's look at more complicated things, at reflection groups. So the first one is the hyperoctahedral group. That's a symmetric group on the hypercube in Rn. So the hypercube has how many? 2 to the n points, right? So it's a permutation of 2 to the n objects, yeah. A lot of them. As an example, well, we're, for the squares, the diagonal group D4, so H2 is D4. Now, question, what's the cardinality of Hn? And that is actually quite tricky. If you don't know the trick, you might get lost into computations here. So here's the trick, the symmetric group of the hypercube. Well, that's the same thing as the symmetric group of the coordinate axis of Rn. So let's take the hypercube center, that's 0, okay? Sides parallel to the axis. Permuting a hypercube is the same as permuting these guys here, like, okay? But it's not exactly permutations, it's a sign permutation. In each coordinate axis you're allowed to flip it too. So this means that, well, we have an embedding into n, and so it's like permutation matrices, but with signs now, because you're allowed to flip axis. So the image of this embedding is exactly the -1, 0, 1 matrices having exactly non-zero entry on each row, each column. So now with this we can count the group. It's exactly a permutation matrices, but at any of the n positions there you have a binary choice of putting a minus sign. So you have n binary choices, so it's 2 to the n times factorial n. This is very nice, okay. And well, now you can actually prove too, I mean, that's just the cardinality, but as it was the case with the diagonal groups, you can say that this is the cardinality of Sn times Z2 to the n somehow. That's what happens, it's a kind of Sn, but you have these binary choices everywhere, and it's not exactly a product. It's like for the diagonal group, it's a semi-direct product. It's a bit twisted, and it's also called this kind of special kind of semi-direct product. It's called the Ruiz product, denoted like this. So once again, this is advanced algebra, it's good to know, but we won't get into this. No, so instead let's go to more complicated examples now. So let's go into the unitary case. So we'll do exactly the same thing now as before. Let's go back. You see, matrices having entries here with exactly like permutation ones. Let's do exactly the same thing, but instead of -1, 1, to put arbitrary roots of unity of order S. So we obtain a group H and S. And well, this is nice because at S is 2, of course, we obtain HN, but at S is 1, what's the first root of unity is just 1, so we obtain the symmetric group Sn. So see, this construction unifies somehow Sn and Hn. That's a very good thing. So in general, I have a certain finite group which is unitary now. It's no longer orthogonal. At S is infinity, you can allow here S is infinity because the group of S is the group of S roots of unity. And when S is infinity, this is by definition the unit circle, okay? So here you get the group 2, it's very interesting. It's called a big complex reflection group containing all these guys here, but it's no longer finite. But we allow this group somehow. It's not really a part of the continuous group philosophy. It's at some point discrete thing. And now, well, the big theorem is that, that's a big theorem from the 70s, that the complex reflection groups are exactly these guys with the parameter added, so you can still impose a condition, this condition that the determinant to a power d is 1. And it stops here. I mean, that's all the complexion reflection groups. The rest are just some exceptional examples. I think there are 34 of them. That's a theorem by Shepard and Todd from the 70s. So, well, under some assumptions on the reflection groups, they're irreducible, something like that. So very, very interesting things. And that's going to be the things to look at. So conclusions, what we did today, yeah, definitely complex reflection groups. These are the groups to be studied. And for the methods we've seen for the symmetric group, that trace and determinant are very interesting to compute. So that's what we'll be doing in the next 2 lectures for the symmetric groups and these reflection groups. Look at traces, determinant, compute their distributions, things like that. So see you soon.